Hi guys, I would like to demonstrate how I would solve this problem number 9 that is assigned as a homework problem. Once you know how to solve this problem, I believe that you should be able to solve all the other problems because they are quite similar. So for convenience purpose, I already copy paste the Taylor polynomial, the nth order here, and the remainder formula. The remainder is for us to find the error. Now the first function is f of x is e to the x times cosine x, and the center is 0, which makes it very nice. And we want to find the p2 and approximate at x equals 0.5. Now you want to certainly take advantage of Mathematica, the technology, to so that you don't have to spend too much time to find the derivative and evaluate function values. So, of course, using Mathematica, leave all the calculation or algebra to Mathematica so that you have a bigger picture of what's going on, and that's more important. So here I already, to save time, I already wrote down the P2. So when n is 2, the remainder right here, right? So we are gonna find the third derivative here. So that's why we have f third derivative xi over 3 factorial times x cubed, where xi is between 0 and x. Now here's how I would take advantage of Mathematica. So we do need to find the f prime, f double prime, right? So how do I find that? This is my Mathematica here. I already defined f of x, which is e to the x times cosine x. Find f prime at 0. This is what you do. So you could do it 2 steps. F prime of x, and you can take a look at what that is. This is your original f of x, and this is your f prime of x, okay? Oftentimes this is not necessary. You really can combine 2 steps together. You can evaluate f prime of 0 like this. Use the syntax f prime and square brackets 0, and sometimes probably I want to add the semicolon so that I don't have to see the f all the time. So f prime of 0 is 1. I'm going to write this down. Okay, I'm going to choose a red. So according to my Mathematica, this is 1. Okay, and let's continue to do the f double prime at 0. So f double prime, you just type this prime symbol twice at 0 and run it. So it's equal to 0 here. So I do know that this is going to be 0. This is going to be 0. Okay, now with that I can quickly find my P2 of x, which is equal to f of 0. F of 0 is actually 1, okay? Cosine 0 is 1 because I can do the algebra quick. If you're not quite sure, you can do f of 0 in Mathematica as well. So which is 1. So it's 1 plus f prime is 1. So therefore the next term is x plus the next term, this is 0. F double prime is 0. So it's going to be just 0. And then so this is my P2 of x. Oops. P2 of x. Now use P2 of 0.5 to approximate f of 0.5. So f of 0.5 is approximately equal to P2 of 0.5, right? Which is 1 plus 0.5, which is 1.5. And then my find an upper bound for error, the true value minus this approximation. So when we say found error bound, that's where this formula comes in, this error formula. So I have to find this guy. So we need the f third derivative at xi. So let's find the third derivative. So my third derivative, don't evaluate that 0 because it's gonna be xi. So therefore I'm just go ahead find the third derivative. So this is the third derivative. Okay, take a look at that. So it's gonna be there's a common factor here, negative 2 e to the x. That's the common factor, right? You can move it out. Once you move it out, this is what you see. Negative 2 e to the x cosine x plus sine x. That's your that's your third derivative. So I'm gonna write this down here. So my R3, let me quickly write this down here. My third derivative of x is gonna be negative 2 e to the x cosine x plus sine x. Please write down the intermediate step when you do your homework. So therefore my R2 of x is equal to, now this is f third derivative of xi. So I'm gonna write this as xi, right? Because this is x, you plug in x. When this is xi, you plug in xi. Times cosine xi plus sine xi divided by 3 factorial, which is 6, times x cubed. Okay, and where's this xi? Xi is between 0 and x. Okay, let's continue. I need to find the error now. So again, this error bound, this is exactly the error. Okay, I want to find an error bound. That means I want to now I'm going to change your color to emphasize. When you say error bound, we actually look at the absolute value of this error term. Okay, so we always look at absolute value. So now because we are approximating 0.5, therefore I'm finding R3 of 0.5 absolute value, which is this guy. So 2 times e to the xi. Well, practice that to write that nicer. Cosine xi plus sine xi. Well, by the way, we can actually, well, if you want to, you can go ahead cancel these two, so that this is 3. Now, x is 0.5, therefore you have to write 0.5 in this case, 0.5 cubed. Don't forget to, don't forget the absolute value. So now this xi, let's make sure xi is in between 0 and 0.5, okay? Why 0? Because center is 0. Why 0.5? Because you're approximating, you just approximated at 0.5. So that's the reason. Now let's continue. So I want to find a bound. And this is 3 is constant, 0.5 is constant. So 3 and this 0.5 cubed, I can quickly move that out of my absolute value sign. So what I really need to find bound is this piece, right? This is what I'm gonna do. I'm gonna make a graph of this function in Mathematica to take a look at where the maximum would occur, the absolute value of the maximum will occur. So in my Mathematica, the plots command. So we type in the function and then specify the domain of the restricted domain. And sometimes this is not what we, it's not that nice, because you see that y doesn't begin with 0. So if you really want to take a look at the whole picture, sometimes this can be done. The syntax is called the plot range with an arrow sign, and this is the x values, the interval for x, and this is the interval for y from 0 to 3. I see that it's from 1 to 2 point something, so that's why I make that 0 to 3. So double check your syntax like previous one. I have one that's purple that tells you something is not quite right, so I have extra bracket sign, so I have to delete it and then run. And then you can see that here the maximum occurs at this endpoint, right? When xi is 0.5. So with that, I can now bound this function. So this is how I will bound. So I'm gonna go back to here. So times e to the 0.5. Why 0.5? Because the graph looks like this, right? This is 0, this is 0.5, and this max occurs right here. So that's why we pick the 0.5 times cosine 0.5 plus sine 0.5. Okay, after the algebra, use your calculator, and this numerical value is your error bound. So now that's it for the first part.